This is going to be our Unit 2 video on dynamics. What is dynamics? In the previous unit, kinematics, we discussed the behavior of particles, the behavior of objects, as the acceleration of said object is constant. What is a constant acceleration? It's an acceleration that doesn't change, meaning it's either, let's say, a constant 9.8 in the case of gravitational acceleration. 0 is a constant, and here in dynamics we will be examining problems in which there is a non-constant acceleration. So let's get into what a system is. Okay, a system is defined as a set of objects, a set of particles, a set of whatever that are participating in an interaction. So let's define what an interaction is. An interaction would be, for example, me taking my fist and punching the wall. Okay, that is my fist interacting with the wall. Two objects, being my fist and the wall, interact. That is an interaction that is internal to the system. If I then take my head and I go over to that wall and I bang my head on that wall, that is an interaction that is external to the system, okay? Because only this wall and my fist were defined as being members of the system. So let me draw a picture of this so we can make it easier to explain. Let's pretend this rectangle is my fist, and this little colored region is the wall, okay? And these are the bounds of our system. This is everything that is included in our system. A system is something you will need to define for any problem you are given, okay? So if I told you that my fist hits the wall, you will need to take a moment, step back, and say, okay, what are the bounds of the system I'm dealing with? What is included in the system that I'm dealing with? The wall is included and my fist is included. One of Newton's laws, Newton's first law, says that an object at rest stays at rest and an object in motion stays in motion until acted on by an outside force, okay? So this wall and my fist will stay stationary until acted by an outside force. What is an outside force? It is a force that is external to the system, okay? An outside force is external to the system. So notice how the system includes the wall and my fist. What is not included in the system is the rest of my body, okay? So the rest of my body can exert an outside force onto my fist and therefore change the position of my fist. So if the system is defined as being the entirety of my body, then my center of mass would be somewhere around here, because the top of my body is a lot heavier than the bottom half. If the system is defined as being the wall and my body, then the center of mass would probably be somewhere around here, being much closer to the wall than my body, because the wall is much more massive than my body. So now that we've gotten our discussion of systems out of the way, let's start to talk about this word that I had alluded to before, forces, okay? The entirety of Unit 2 is based on forces. What is a force? When a force is essentially a push or a pull on something. If I push on this wall, that is a force my hand is exerting on the wall, okay? If the system is defined as the wall and my body, and that means that this force is internal to the system. If the system is defined as just the wall, it means that this force is now external to the system. So the first type of force we're going to cover is going to be the gravitational force, often abbreviated as capital F sub G. The gravitational force is what's called a field force. What is a field force? It is a force that acts on objects without directly touching them. If I jump up in the air for a split second, I am not touching the ground, okay? But even though I'm not touching the ground, the force of gravity is still acting on me. Therefore, it does not need to contact me in order to exert said force. The force of gravity on Earth is equal to the mass of an object multiplied by the gravitational acceleration, which is a constant here on Earth, g. So if my mass measured in kilograms, I don't know what my mass is in kilograms, maybe, well, let's just say it's 100 kilograms for simplicity's sake. My mass is 100 kg, and the acceleration due to gravity is 10. That means the force of gravity exerted upon me is 1,000, the unit of force being Newton. Okay? Now, given this equation, the force of gravity is said to be your weight. Force of gravity is the force that you exert on a scale when you weigh yourself. You have a weight on Earth because there is a gravitational acceleration on Earth. You do not have a weight in space because there is negligible gravitational acceleration in space. So you don't weigh anything in space, okay? But just because you're in space has nothing to do with your mass. Mass is a measure of how much stuff is inside you. More specifically, it's a measure of how many subatomic particles make you up and what the energy of those particles are. So the amount of particles that make you up doesn't change whether you go from Earth's surface to orbit, but your weight does change. The force that gravity exerts upon us is pretty strong here at the surface of Earth, and it gets progressively weaker as you travel further away from Earth. G is the acceleration due to gravity at Earth's surface. And you might be asking yourself, well, wouldn't that mean that the acceleration due to gravity would be different at sea level than it would be on the top of Mount Everest? Yes, you're correct. It would be different. But compared to the distance between here and the International Space Station, the distance between here and Mount Everest is a very, very, very small distance relative to here to the International Space Station. So we're saying that the difference in acceleration between 2 points in differing elevations on Earth's surface is so small that it is negligible. And by that token, we are allowed to use G as the gravitational acceleration for most points near Earth's surface. Contact forces. As the name might imply, these are forces that are only applied when you contact something. Your friend can't shove you down the stairs without touching you. You need to physically touch your friend in order to shove him down the stairs. Your friend gets hurt because the stairs physically contact his face. That force cannot be exerted without some contact. 3 main types of contact forces we're going to cover in AP Physics 1 are the normal force, the tension force, and the frictional force, denoted as such. The normal force. What is a normal force? If I push on this wall with my hand, the wall doesn't fall over. Why doesn't it fall over? Because the wall is exerting a normal force back onto me. To resist my motion, that means the net force is 0 and it doesn't move. That's an important clarification we need to make. When we take into account all of the forces acting on an object, that is called the net force. And if the net force is 0, the object cannot accelerate. Now, acceleration is different from velocity. What do I mean by that? It means acceleration is the rate of change of velocity. So if there's no acceleration, it means velocity is not changing. If velocity is not changing, then you remain at constant velocity. This is the special case where our constant velocity is a 0 velocity. If this marker was moving and it had a 0 acceleration, then it would continue moving at the same exact velocity because the velocity isn't changing. The tension force. Tension force is exerted when you pull on something. Normal force is exerted when there's a push. Tension force is exerted when there's a pull. Normal force was pushing. Tension force was pulling. Frictional force is sliding. When I slide my hand across the surface, I notice that there is a force trying to resist this motion. That's why we call the frictional force a resistive force. All this talk about forces now let's really crystallize how these forces and systems are governed. The 3 laws of motion from Isaac Newton. Law number 1. An object that is at rest stays at rest, and an object in motion continues in motion at a constant velocity unless acted on by an outside force. So if we were to express that numerically, we would say that when the acceleration equals 0, a velocity is constant. If velocity equals 0, position is constant. Only if net acceleration does not equal 0, then velocity is not constant. Number 2, Newton's second law states that the net force exerted on an object is equivalent to the mass of the object multiplied by the resulting acceleration in that object. If I were to push this marker, the marker's velocity just changed. Initially it was stationary, and with my pushing, the velocity is now positive. It is now a number. So I exerted a net force on it. And because the velocity changed, that implies that there is now an acceleration. Okay? This equation governs the relationship between the magnitude of the force you exert and the magnitude of the resulting acceleration. I could put this marker on a scale that would measure the mass of the marker, and once I deduce the mass, I can relate force to acceleration. Newton's third law. Every force is opposed by an equal and opposite force. Meaning, if I push on this wall, the wall is going to push back on me to the best of its ability, okay? That, in this case, when I push on the wall, the normal force of the wall pushes back on me. That's why when you fire a gun, this is the best example, when you fire a gun, there is recoil. Okay, when you pull the trigger, the bullet is accelerating out of the barrel, but the recoil is forcing back on your shoulder. The gun exerted a first force on the bullet, and the bullet exerted a force on the gun, and that force exerted on the gun is now transferred to a force exerted on your shoulder. The force of gravity is another good example. We're going to cover the force of gravity when we cover orbital dynamics. Everything with a mass exerts gravity. The reason that the Earth's gravity is so powerful is because the Earth is really massive. There's a lot of particles in the Earth. But this marker also has mass, so it will exert gravity. So when the Earth exerts a gravitational force on the marker exerts the exact same gravitational force on the Earth. That is a really cool equivalence, because that states that if you weigh 120 pounds on Earth, it means that the Earth weighs 120 pounds on you. That's a cool fact, isn't it? Anyway, when we're talking about Newton's laws, we're talking about forces. And you've heard me talk about this thing called net force a lot of the times. What is net force? Net force is what you get when you add up all of the force vectors acting on an object. And in order to express the force vectors, we use something called a free body diagram. A free body diagram is a diagram with a dot at the center representing your object, your participant, as I like to call it. And on that dot, you will draw the force vectors acting on it. Remember, a vector is an arrow that has direction. It points in the direction of which the force is applied, and the length of the arrow corresponds to the magnitude of force being applied, meaning more force is conducive to a longer arrow. Let's call this my marker, okay? Let's call it a marker that I am holding in my hand like this. Let's just consider that example first. When I'm holding a marker in my hand on Earth, I'm going to have a gravitational force. And we label our forces. This is going to be F sub g, the force of gravity, okay? Now let me show you again. If I hold my marker like this, marker isn't moving. Every time you see that something is not moving, it means that the net force is 0. I wrote that somewhere here. If the net force is 0, velocity is constant. In this case, the velocity is a constant 0. If the net force is 0, it means that these two vectors need to cancel out. What is the remaining force acting on this marker? The marker pushes down on my hand pushes back up on the marker, which is the normal force exerted by my hand on the marker. Remember what I covered in the introductory video, we add vectors tip to tail. If I draw the gravitational force vector and then I add to it the normal force vector, I come back to the original place I started. Therefore, the net force, the addition of the two forces, is 0. You calculate net force not by adding the magnitude of each force, not by adding the numerical value, but by adding the vectors. Okay? If the normal force is pointing upward and I define the positive direction as being upward, let's say this exerts a force of plus 10 newtons. That means the gravitational force exerts a force of minus 10 newtons on the marker, because down is defined as the negative direction. So if I add 10 to negative 10, 0. That is why direction is important when we consider net force. Let's say I'm holding my marker in my hand, and with my other hand, I am pushing the marker along like this. Okay? Notice what just happened there. My velocity was originally stationary, and it changed to become a positive velocity if we define that direction as the positive direction. So because velocity changed, it means we needed to have an acceleration. And if we had an acceleration, it means we need to have a net force. Okay, let's draw the free body diagram of the forces acting on the marker in this scenario. Again, you're going to have the force of gravity going down. Nothing changed about the force of gravity. So that means we're going to have a normal force pointing up of the same magnitude. Well, hold on a minute, Meek. That's going to mean we have no net force. You're right. There is no net force in the up-down direction. 0 net force in the up-down direction. That's why when I pushed the marker, it didn't move up or down. Because if we consider only the up-down direction, there is 0 net force. But when I add the force exerted by my hand, force applied, we discover that even though there is 0 net force in the up-down direction, there is a net force in the x direction. Up-down direction being the y direction. Okay? So I have a net force in the x direction. Let's assume that the mass of this marker is 1 kilogram. We're going to say that 1 kilogram times the acceleration of the marker, which was about 1 meter per second squared, means that we exerted a force of approximately 1 newton on the marker when we did that. The force of friction is interesting because the force of friction is a resistive force. There's an equation that governs this force on your reference table. If you will humor me and take it out, you'll see that counting down from the top, you have your 3 kinematic equations, followed by the Newton's second law equation, which is written on your reference table as the acceleration vector is equal to the sum of the force vectors divided by the mass, which is equal to the net force vector divided by the mass. Okay? If we rewrite this equation, we multiply both sides by mass, you get the net force vector is equal to the mass of an object multiplied by its acceleration vector. And beneath that equation, you are given that the magnitude of the frictional force vector is less than or equal to your coefficient of friction mu multiplied by the normal force vector, magnitude of the normal force vector. Let's unpack that equation. The coefficient of friction is something that will be given to you. Coefficient of friction is effectively a constant that defines how frictiony a surface is. Higher coefficient of friction means that more friction will be exerted upon you as you try to move across it. For example, a carpet will have a greater coefficient of friction than this whiteboard. This is a lot more slippery than the carpet. So the whiteboard would have lower coefficient of friction. So you would take your coefficient of friction, let's say in this case it's 0.5, and you would multiply that by the normal force. Well, how do we find our normal force? We said that our net force in the xy direction, sorry, not the xy, our net force in the y direction was 0. How do we know it's 0? Because our marker did not accelerate in the y direction. That means our forces are balanced, which means that the downward force equals the upward force. It means that force of gravity equals force normal. What is the force of gravity? Force of gravity equals mass times acceleration, like we covered up here. But in this case, in this special case, the force of gravity is the mass times what acceleration? The gravitational acceleration. So we can say that our force normal in this case, the magnitude of our force normal is equal to our mass times the gravitational acceleration g. And we would say that the magnitude of our frictional force is less than or equal to the coefficient of friction multiplied by our normal force, which we defined here as mg. That's how we would find our frictional force. Now, what does this less than or equal to sign? The less than or equal to sign defines the difference between static and kinetic friction. So this is my marker box. If I were to put my eraser on top of that marker box and I were to use my hand to exert a force on it, you would see that it's at if I just push it a little bit, doesn't move. What's the matter? I'm exerting a force on it. Why isn't it moving? That's because the frictional force, being a resistive force, is acting on the eraser to oppose the force exerted by my hand. So it is not moving because there is friction between the eraser and the box, okay? However, if I push harder, I can overcome that friction, meaning that the frictional force has a maximum value. For a very small applied force, I can apply a very small applied force, it won't move. I can slowly increase my force, and it still won't move because the frictional force is simultaneously increasing to oppose the frictional force. The frictional force is simultaneously increasing to oppose my applied force up to a certain point where my applied force becomes so great that it overcomes the maximum frictional force. The frictional force that occurs when the object is not in motion is called static friction. The frictional force that occurs while the marker is in motion is called kinetic friction. Kinetic friction is a constant value. Okay, kinetic friction is defined as the force of kinetic friction equals the coefficient of kinetic friction equals the coefficient of kinetic friction times the normal force. Static frictional force is less than or equal to the coefficient of static friction multiplied by the normal force. The maximum static frictional force that can be exerted is greater than the maximum kinetic frictional force, such that if we were to graph applied frictional force on the y-axis and we were to graph the force applied by my hand on the y-axis, on the x-axis, as the force applied by my hand increases, the frictional force applied by the box increases proportionally in order to oppose the force exerted by my hand. Okay? And the frictional force, static frictional force, will continue to increase up to a maximum value, and it is at this maximum value that the eraser starts to move. And then once the eraser starts to move, we transition from static friction to kinetic friction, such that the force applied by kinetic friction is less than the maximum force that can be applied by static friction. So now that we understand the frictional force, we can consider the very popular physics problem of a block sliding down an incline. We got a block right here. We've got an angle theta right here. And we are given the coefficient of static friction, mu sub s, equals 0.85. Coefficient of kinetic friction, mu sub k, equals 0.6. Let's cover the free body diagram that is characteristic of this block. The normal force is always applied exactly perpendicular to the surface. So in this case, of course, let's start with gravity. There's gravity acting on the box. So we draw a line straight down signifying force of gravity. Any time and every time two surfaces are in contact, there is a normal force. Normal force would be exerted at the angle that the incline is present at. So that would be our normal force. Let's just say that the block is not sliding down the incline. That would mean we have a frictional force, and because it's not sliding, it would be static friction. acting opposed to the direction in which the block would slide. So since the block would be sliding down in this direction, if there were no friction, the frictional force must oppose that movement and pull in this direction. So that's going to be our free body diagram. Let's solve for the frictional force, because that also involves us solving for the normal force. What would be the normal force in this case? Well, first of all, we are given that the block is not moving. Therefore, we know the net force is 0. Since it's not moving at all, we know that the net force in the x direction is 0, and the net force in the y direction is 0. So like I said before, we're defining the incline as our x-axis, and we're going to define the line perpendicular to the incline as our y-axis. Remember what I said before? Whenever we have a vector that is not collinear with one of our coordinate axes, we can resolve it into components. The force of gravity, has a component that is collinear with the x-axis and a component that is collinear with the y-axis, pointing in those directions. This angle here between our y-axis and our gravitational force is theta. It's the same theta that we identified down there, okay? It's a pretty long explanation for me to justify to you why this angle is the same as that angle, so just trust me on this. Whenever you see this problem, the angle between your gravitational force and your y-axis is always going to be the same as the angle denoted to you here in the incline. If we want the x component of our gravitational force, we're going to need opposite over hypotenuse sine of theta times the force of gravity is equal to the x component of the force of gravity. We're going to denote that as the force of gravity sub x. If we want the y component of our force of gravity, that's going to be the force of gravity times cosine theta equal force of gravity sub y. Now we know that the normal force and the y component of the gravitational force are going to be completely balanced. How do we know that? Because the block is not levitating off the incline. If it were levitating off the incline, it would be normal force is greater than y component of gravitational force. And if it were falling through the incline, it would mean that y component of gravitational force is greater than normal force. So since neither of those two things are happening, the two forces are equal. So we can say that the force of gravity sub y is equal to our normal force. And if we resolve that back into these numbers, we say that the force of gravity times cosine theta equals our normal force. And more specifically, what is the force of gravity? It's mg. We can say mg cosine theta equals our normal force. Now that we have our normal force, we can solve for the static frictional force acting on the block. We know that the static frictional force, let me make sure you guys can see, is less than or equal to the coefficient of static friction multiplied by the normal force. But we also know that the frictional force is working to oppose the x component of the gravitational force, because we know the block is not sliding along the incline, which means the force pulling it up the incline, the frictional force, has to balance the force pulling it down the incline, which is the x component of the gravitational force. So we can say that the force of friction equals Fg sub x, which is the same as, where did I put it? Fg sine theta, which is the same as mg sine theta. That's our frictional force. So if we know mg sine theta equals frictional force equals the coefficient of static friction times the normal force, we now know that mg sine theta equals mu times our normal force, which is mg cosine theta. And if, let's say, we wanted to solve for mu, our coefficient of static friction, we would say that mg sine theta over mg, can you guys see this? I think you can see this. Mg cosine theta equals mu. So let me bring that up here. Mg sine theta over mg cosine theta equals mu. M's cancel, G's cancel, sine over cosine is tan. Therefore, tan theta equals mu. So because this is a less than or equal to sign, this equation only holds current at the maximum static frictional force or at the kinetic frictional force, where this turns into an equal sign. That's the incline problem. A much simpler problem that allows us to better illustrate the concept of systems and internal versus external participants is the two-block problem. So this usually shows up as a multiple choice, but it's very useful to understanding systems, okay? You are given a problem such that you have one block, 10 kilograms, you have another block of 8 kilograms, and you have a force, an applied force, pushing them to the right. So in this case, we would define our system as being the two blocks. And if we define our system as being the two blocks, that would then mean that this applied force is external to the system. Since these two blocks are being acted on by an external force, it means the center of mass is moving. Remember, the center of mass just being a representation of where the mass of our system is averaged or concentrated, okay? I had two markers of equal mass. Let me get my markers. If I had two markers of equal mass, their center of mass would be exactly between the two. And in this case, the center of mass has not moved because they are still an equal distance from the center, right? Now, if this marker were to start moving, that means that the center of mass would start moving in this direction, because the average position of all the mass is further moving in that direction. But if one moves in this direction, the influence on the center of mass by this marker is canceled by this marker if it moves in the opposite direction. Okay, so we have an external force acting on the system. If an external force is acting on the system, it means the system's being accelerated. So we can say that our applied force is equal to our mass times the acceleration of our system. The total mass of our system is what? It's 18 kilograms. That means the applied force is 18 times the acceleration of the system. Let's say the applied force is 100 newtons. That means that 100 newtons equals 18 times the acceleration of the system. Okay, so let's plug that into a calculator and solve for the acceleration of the system. Let me ask you guys something. Is the acceleration of this block different from the acceleration of that block? No. If I push two blocks, one block is going to move exactly the same amount as the other block, because acceleration is nothing more than the rate at which your velocity is changing. And these two will move attached. They will move simultaneously in the same manner. Okay? So if we take 100 divided by 18, that means the acceleration of our system is going to be 5.56, which means that the acceleration of the 10 kilogram block is going to be 5.56. The acceleration of the 8 kilogram block is going to be 5.56. But let's examine the forces that are being exerted inside the system, okay? If I push the 10 kilogram block, that means the 10 kilogram block now needs to push on the 8 kilogram block. That is the normal force between the two, okay? And since every force is met with an equal and opposite force, that means that there is now a normal force between the 8 kilogram block and the 10 kilogram block. Let's consider the free body diagram of the 10 kilogram block and the free body diagram of the 8 kilogram block. The 10 kilogram block has the force applied acting on it. It has the force of gravity, the normal force being pushed up by the table that it's resting on. Oh no, I'm sorry. Force normal, the arrows must start on the center and push away from the center. So this would be our applied force. And then the normal force exerted by the 8 kilogram on the 10 kilogram would be present here. I'm going to denote this as F of the 8 on 10, 8 kilogram acting on 10. Now if I move the free body diagram of the 8 kilogram block over here, we are going to get, again, your force of gravity, your normal force, and you're going to get the normal force of 10 on 8. I'm sorry, this arrow should be considerably larger because we don't want to give the illusion that these forces are balanced because the block is moving. These forces are not balanced. So we determined that the acceleration of the whole system is 5.56 by using the mass of the whole system. We can determine the normal force exerted by block 10 on block 8 by looking at the net force in the x direction, which is the normal force of 10 on 8. Okay? And that net force in the x direction is equal to the mass of block 8 times the acceleration of block 8, 5.56. If we do that on our calculator, we get 8 times 5.56 gives us 44.8. So we now solve that the normal force of block 10 pushing on block 8 is 44.5 newtons. And by Newton's third law, that every force is met with an equal force, we know that the magnitude of 8 on 10 equals the magnitude of 10 on 8, which is equal to 44.5 newtons. And therefore, we can say that the net force in the x direction on block 10 is equal to the applied force minus the force of block 8 on block 10. Using this, we can solve for the net force on the block 10, which is going to be the applied force of 100 newtons minus force 8 on 10, which is 44.5. Therefore, the net force on the 10 kilogram block is 55.5. Okay? And that should correspond with the Newton's second law equation on this block. If we were to write the net force acting on the 10 kilogram block in the x direction, that would mean that that is the mass of the 10 kilogram block times the acceleration of the 10 kilogram block, 5.56. So that confirms our calculation. This is the result of rounding, but we can see that 10 times 5.56 is approximately 55.5 or 55.6. You will encounter minuscule differences like that because we are rounding in physics. Okay, thanks for watching, guys.